decided to invite me for this school. That's the third time I participate in a mechanic school here in Rio, and it's also a great pleasure to be here. Okay, so I will try to discuss with you instrumental aspects of correlated F-electron systems. And since this is a lecture, I will try to introduce some basic aspects of F-electron from the beginning, from the Hunter rules to crystal fields and everything, and then I will try to connect these basic aspects to more important mechanisms and exciting properties of this compound. So before I start, so as I mentioned, I am from Campinas. I want to know for the students that came from abroad, so how many of you actually knows where about in Brazil Campinas is? Okay, so I have an excuse to show Brazilian map here. So we are here enjoying the beautiful beaches at Rio de Janeiro, and Brazil has a very long seashore. You can see that. You can see there 8,500 kilometers. The population of Brazil is nearly 200 million. Campinas is in the São Paulo state here, and it is about 100 kilometers northeast from São Paulo capital, São Paulo city. Great São Paulo has 10 million of inhabitants. Great Rio has around 12 million, is that correct? I got from the internet, I guess it's correct, right? And Campinas is a very boring place. So that's why it's very good to work there. So we don't have distractions. So we work very hard. So that's the beautiful beaches of Brazil, right? So some pictures that similar to what you have seen around, but then you go to Campinas, you have nothing. It's very boring. Well, you know that the mayor made that lake so he could sell all the lands around in his benefit. So you know it's very complicated. Right? So that's Campinas State University. That's our university. So it's a reasonable new university. It's only 40 years old. It has 3,000 students. It has an area of about 4 square kilometers. So that's my group there. So we belong to the Magnetic Optical Facilities group. And we have many kinds of machines there. So we have a PPMS, which is a commercial system that can measure all kinds of magnetic properties, like heat capacity, magnetization, resistivity, thermal conductivity, under pressure, so on. How many of you are instrumentalists? Okay, how many of you does own a PPMS in your group? Okay. I squeed.
Do you have a squeeze?
I have a squeeze.
Not a PPMS.
Okay, all right.
Okay, don't make confusion. Okay, we also have two squeeds, right? That goes to different fields, a 7 Tesla and a 5 Tesla one. We also have a Raman laboratory, Raman spectroscopy, so you can do Raman from 1.6 Kelvin to 800 Kelvin, also as a function of magnetic field. We also have a lot of X-ray facility and furnace to make samples, and a very nice cabinet with the periodic table design. So we try to keep all these drawers full of elements so we can make our own samples independently. Of course, the ones that we can keep in the drawer, right? And it's not very common. So how many of you have electron spin resonance spectrometer in your lab? How many of you have heard about electron spin resonance? Okay, that's better. So we can do that also in our lab. And now, recently, we got money, we got funding to have an NMR laboratory also there, and NEQR. So we're going to have ESR and NMR at the same lab together with all the other techniques. And we can, I'm talking about ESR because in my second lecture, I will actually use ESR to discuss with you the role of the d electrons in the nuclides, something that we can learn exclusively from ESR. Very important results. And so we have different, oh, I'm sorry. we have different fields that we can use in our ESR spectrometer, and in that second lecture I will explain in detail how we can extract information for ESR. Okay, so we also have in Campinas the only synchrotron laboratory of South America. Is there in Campinas, our neighbor. And you have now 18 working beam lines in the synchrotron, and we have a new project to build a second one, a next generation synchrotron, just next door of this one. If someone is interested in learn more about this, you can visit these websites there. So like I said, it's not a very entertainment city, but it's a very good city to work and to have a lot of productivity there. Okay, so I will start to discuss physics now, and my lecture has this outline. I will start with F electromagnetic properties from the basis, and then I will give some introduction to the heavy Fermi materials, which they have F electrons, and then heavy Fermi superconductivity means similar crystal structure. So I will try to discuss what's important in a crystal structure that may give to that structure the property to be a frequently host for heavy Fermi superconductors. And then I will try to discuss the role of dimensionality of those crystal structures and relate them to a very basic properties of the F electron. And then in my second lecture, I will try to make a connection between the behavior of the heavy Fermis to the behavior of the pnictides. We will try to make a correlation between the whole of the site symmetry and the crystal structure and the magnetic superconducting properties of both systems. I will try to show you that there are some arguments and some aspects that they can be indeed very similar. Okay, so I will talk about these elements here, right? The lanthanide series. Right, so we start this kind of atoms from lanthanum here, which has no electron F, and we go along the lanthanide series until lutetium, which has the full F shell. Between cerium and ytterbium, all the electrons go to the F level. You are feeling the F level, and that gives you different kinds of spins there. So chemically, they are usually 3+, they have the valence 3+, and like I said, they have incomplete F shells. And the F shells, they are inner orbitals in the atoms, right? So they are partly shielded by the external orbitals. So that makes the F electrons, they feel much less the crystal field environment. So they couple first to the orbital. So the spin orbital coupling is larger than the crystal fields. So that makes the total angular momentum J the good quantum number for F electrons, right? Okay, so to determine the spin orbital ground state, you just use the Handel's rules. You couple the electrons to give the maximal total spin, and you choose the maximal L, and if the shell is more than half full, the highest total angular momentum state will be, the lowest will be L plus S, the modulus of L plus S, and otherwise the lowest will be L minus S. So I'm just show some of the words that I'm going to use in my talk. So cerium has one F electron, so it has S equal 1/2, L equal 3. So it's less than half full, so J is L minus S, so the J for cerium is 5s. I'm going to use the gadolinium, which is here. Look at the gadolinium, it has S equals 7/2, it has no L, right? So along the arrows, gadolinium is the only one that has a pure spin, right? It has no L contribution. That's important, I want to keep that in mind. I want you to keep that in mind. So what happens when you have your earth in a crystal? You have the Coulomb potential of the charge, right? So that will lift the degeneracy of the multiplet J and also can create some spin anisotropy. So how many of you have ever done crystal field calculations? In your work or during your graduate course? Will you raise your hand, please?
Chemistry, not yes.
Okay, so this part may be a little bit boring for you, but I will. Oh, I know Aline has to. You has done in a much more sophisticated way, right? But I want just to show a few steps how you consider the crystal fields, right? So, so to consider crystal fields, you need to consider the potential from the surrounding charges, right? And for that, the most simple idea is to use point charge model. So what you do, you calculate the electrostatic potential at a given point of space, given by this lowercase vector r, and you have a charge in the capital R vector, and you have a kj car there. And you need them to calculate the energy associated with all the charge around your magnet ion that's close to the origin, right? Okay, so it's much more convenient to express this potential in terms of polynomials that are related to the harmonic of the spherical harmonics. So here we have the spherical harmonics, and you can construct the tesseract harmonic to avoid imaginary parts in that series. So I'm just trying to write the potential of the charge in terms of functions that I know how to use the symmetry to avoid imaginary terms and to define zero terms. So when I get that series and I use the symmetry of my site, I can do that very easily in point charge model for three configurations. Charge placed at the corners of a octahedron, or placed at the corners of the cube, or corners of a tetrahedron. In these three cases in cube symmetry, you can solve the problem and you can get the crystal field parameters from the charge very easily. So what you do, you use the symmetry and then many terms of that series is just zero. So we will end up with the fourth term and the sixth term in the series. Okay, so you have only these two terms in cube symmetry. And these coefficients that we call the crystal field parameter, there depends on the side symmetry, the distribution of the charge, and the distance of the charge that goes here, right? Okay, but the interesting point here is that when you try to extrapolate this for any particular charge distribution, what you do is to write your operators that are in Cartesian coordinates. You apply the Wigner-Eckert theorem, and you can write them in terms of angular momentum operators. And you do that because you can apply then your Hamiltonian to the multiplet J, and you know how your operators act in that J. So when you do that, you have the Klopschen-Gardner coefficients, and then your crystal field parameters here will now depend on J. So that's an important thing to keep in mind. When you make the transformation from the charge crystal field parameters to the equivalent operators, the operators depend on J. So you cannot compare the crystal field splitting between different Hertz, for instance, because B depends on the Hertz. So believe me or not, many of the colleagues I met in my life didn't know that. So here, so you can write this general crystal field parameters now that are J dependent. But you know very well how they act in a multiplet J. So it's very easy to calculate the effect of the crystal fields now. So for instance, you can do that in serial, which is very easy. You can do it by hand, and you can apply these equivalent operators here. They are written in terms of J, and you can get for a table how they depend on J, and you can make a 6x6 matrix from serial. It's very easy, and you can diagonalize that matrix, and you get, for cube symmetry, you will get two eigenvalues, right? Two different energies, and two different states. Which one they are? The gamma 7, which is a doublet, two-fold degenerate, and the 5/2, which and the gamma 8, I'm sorry, which is a quartet. So here we have in cubic symmetry that the cubic crystal field, we split the degeneracy of a J equal 5/2 in a quartet in a doublet. Okay? Okay, so why should I know that? How can this affect my experiments or the properties I want to look at? So those of you that you have a PPMS, right? How many of you can measure heat capacity in PPMS? So how many of you have seen a shock anomaly? Okay, so that's one thing that, good. I'm sure you have seen it. Okay, sure. You don't have a PPMS, do you? Okay.
Yes, you have.
Okay.
Which one is the ground state, the quartet or?
Depends on the parameter, of course.
Depends on what?
On the parameter, on the sign of the parameter.
But in general, the example will depend on the type of compound with where the zero is?
Yeah, so actually you make a question that remind me to make the following comment. Let's assume I made a very simple, I described a very simple model for the parameters, right? Only point charge. But some of you may say, how about the conduction electrons? Do you think they should participate in the crystal field? Should they affect the crystal field?
The electrons which are part of the lattice sites, right?
Of course, right? So, but how about the symmetry? Would they keep the same side symmetry? Or should they add more parameters? So that's a very special thing. You can go to a cubic metal, or a cubic insulator, or a cubic semiconducting, and the crystal field effect will also be given from this symmetry. But the parameter can change the sign, or can change its values when you go from insulated to metal. So how is that possible? How can the conduction electrons keep the same symmetry? So usually we got the answer for that in early ESR work.
Maybe they just pop between the atoms because they're already there. So
Yeah, but they're itinerant, right? But you are thinking in the right direction. When they create the potential, they occupy virtual bound states at the atom to create the potential. And that was seen by electron spin resonance. The effect of was shown by the people from our former advisor in the early 70s and then in early 80s, also in many materials, that they could track the change of sign of the crystal field parameters by going from insulated to metal, and they could identify by the data that the electrons, when they interact with the spin, they are occupying interbound state at the atom. So you keep the symmetry, right? So you are going in the right direction. Okay, so that's good because we can use the cube crystal field Hamiltonian or the tetragonal one for any material. The only thing you should care about is the value and the sign of the parameter. So you can go from gamma 7 to gamma 8, changing the sign, right? Okay, so it can affect your specific heat, right? Because you can have a magnetic specific heat, and the specific heat will depend on the degeneracy of the levels, right? So you can calculate your partition function and your free energy and your specific heat. So it's a magnetic specific heat. When you depopulate your crystal field levels, right, you can have an anomaly like that, which is called a shock anomaly in specific heat. Okay? So it can also affect your magnetic susceptibility for the same reason, right? At high temperature, even for a paramagnetic material. you have your earth there, you calculate the magnetic stability, right? It's a paramagnet ion. But your current constant, you're going to change as a function of temperature, right? Because you are depopulating the levels. So you can see that from departures to a linear Curie-Weiss behavior in the inverse of the magnetic stability. So you can see small departures here that you can fit, right? Using different crystal field scheme and get the scheme that will give you that departure. So that's very complicated to do only by magnetic stability because you can have different sets of parameters for your fitting. But you can usually change your earth, make it consistent, fitted, and try to relate many different properties that will be affected for the same scheme to be sure that we're doing something right. Or you can go and try to measure directly by an electron neutral scattering, for instance. But sometimes you don't need to do that because you can get from your own measurements. But the important thing that if you go to lower symmetry, crystal fields can become more and more important, and they can create effects in your data that can create some confusion. For instance, here I'm showing the magnetic stability for tetragonal compounds. They are praseodymium-based tetragonal compounds. And they are non-magnetic at all because they have singlet ground state. Praseodymium is a non-Crumer ion. So praseodymium can have singlet ground state with no spin. So if it's a ground state, it will be non-magnetic. Depends on J. If J is smaller than splitting. But we can have a lot of features in the data that looks like magnetic ordering or saturation just because of this level configuration. So one should be aware when you're dealing with earths and seeing a lot of anomalies in your data that they may have a very simple explanation sometimes. So what happened when we start to have magnetic ordering? So how the crystal field will affect now magnetic ordering? So if we start to have a lattice of earths and a metal, let's use a metal because I'm gonna talk about metals, but it could be an oxide. You could have any kind of exchange between the earths. So we are going to start to have a magnetic interaction, and that will tend to order the spins of the earths, right? But the crystal fields will define the anisotropy with respect to the lattice, because J will define the relative orientation between your spins, but it's the crystal field that defines the anisotropy with respect to the lattice. In other words, the direction of the magnetic moment, right? So you can have the same compound, the same family of compounds that you can change only the earths, and you can have different sets, different kinds of magnetic structures, only because of the effect of crystal fields and the direction of the spin. And that's very important for the particular problem I want to address. So when you go now to serum and ytterbium, I'm sure Piers will explain all the details and all models for this particular items. But I just want to show you, when you go to this, right, we have a very important interaction that becomes predominant and you need to care about, right? So when you go to serum and ytterbium, they have spin valence instability because they are close to fill or empty the shell. So the serum 4 plus is a non-magnetic state, and the ytterbium 2 plus also is non-magnetic. And the energy between the serum 3 and serum 4, or ytterbium 2 and ytterbium 3, are close to each other. So what happened is that we have your, I forgot I have this in my own. So you can you have your F level very close to the conduction band. So the exchange between the localized electron and the spin is much stronger for these two than for the others. So the F electron is close to the firm surface. So that gives you a very strong and antiferromagnetic interaction between the localized electron and the conduction band. And also, depends on the materials and depends how is the width of the F band, you can also have a very strong hybridization between these two, and the F electron can become itinerant. It can actually go to the conduction band, right? Okay, so that's the underlying physics of the Kondo effect, right? That was first seen by Kondo in his paper about the resistivity of gold when you have a magnetic impurity. So he used the same interaction, that strong ferromagnetic interaction, to explain why the resistivity showed a minimum and then start to increase at low temperature. So that's because of the magnetic scattering of the conduction band. By that, magnetic impurity start to dominate at low temperature with respect to the phonons. And they also proposed that at very low temperature, the conduction band, the conduction spins will compensate completely the spin of the impurity and will create a non-magnetic state, very strong coupled non-magnetic state. And when you have a lot of impurities in your lattice, you go from a Kondo impurity model to a Kondo lattice. And in that situation, you can have the scattering of each site where you have a spin. This scattering can become coherent below certain temperature. So that means in each site we have all this scattering happening coherently in phase. And that makes your resistivity, that is a single period like until certain temperature, will start to drop again, go to the very low value where you recover actually a non-magnetic state in the regular metal temperature dependence.
So where is T coherence? Is that the maximum?
So yeah, so that's this behavior is associated with TK, and T coherence is close to the maximum. Well, it's not. I mean, I will tell you later. The maximum can be affected by other aspects, but it's close to the maximum, right? In a convalescent model with no other contribution, you would be at the maximum. But in a real material, you can have other effects. Okay, so how about the RKQY? So you have a material that you have a magnetic interaction and you have a Kondo effect. So what's going to happen with this material? So both interactions will be present, right? You need to figure out how you treat them. So I will gonna use a very simple model. You know that we have a more complete models now, but I will only use this model to say that depends on the value of J in the base of states. We can have a magnetic state for a Kondo lattice, right? Where the RKQY will dominate over the Kondo effect. But if you increase the product of J to the dense of states, you can have a particular value that the energy scale associated with the Kondo interaction, which grows exponentially, can dominate over the RKQY. So we start to suppress the spin of your local moment, and you can kill magnetism, right? And you can go to a metallic state with no or compensated spins. So in that regime where you completely compensate your spin, your local moment, we have all the entropy of the F electrons in the conduction C. So what you have here, you have a renormalized metal where all the temperature dependence of your state follows a regular metal, but with renormalized coefficients. So you have a Pagliuso bit, but you have an enhanced value of the chi naught compared to a regular metal. You have an enhanced gamma and enhanced A. And those are related to enhancement of the effective mass, and that's why these compounds are called heavy Fermi. So in F electrons, you can have Kondo effect, heavy Fermi behavior associated with this, crystal fields, and magnetic order. All of that together. So what happened to the crystal fields in presence of Kondo effect? So that's a very difficult problem. I'm just showing you a very simple effect that one could imagine, that the effective Kondo temperature will be affected by the presence of the crystal field splitting. If imagine that the conduction C, the conduction electrons want to compensate the spin, they will compensate the spin at lower temperature if the size of the spin actually decreases with temperature, right? So you can just have a renormalization of your effective conduct temperature because your value of J was actually decreased by the presence of the crystal field. So you can imagine just a shift of TK, effective TK, due to the presence of the crystal field spring. Okay, so I know that was very boring because I tried to remind you about a lot of basic stuff. So now I will try to connect all I said to materials that have been studied a lot in the last 10 years, and they show very exciting properties compared to the pnictides and to cuprates. I want to convince you that. But before I go on, I want to show you that sometimes even basic physics like crystal fields can reveal very exciting properties. So when you look at me now, I don't know if some of you would guess this. So I used to be a bass player in a very popular rock band during the 90s, right? Very popular. Well, come on, let's be honest here. Very popular, at least in Campinas, and near some other states, okay? So here I am, wearing a Alsatias t-shirt, which is a Brazilian rock star. And I know that the picture is not very appropriate, but don't worry, everybody is over 21. Okay, so don't worry about it. So we are waiting for going on the stage to open for a very famous Brazilian band, which is called Ira. The Brazilians know about Ira, right? Please help me here.
The one's over 30, maybe.
Over 30, okay. So we were waiting to open for Ira, right? And you can see here, you can probably, the Brazilians can recognize Eduardo Scanduva, which is the guitar player of Ira, here with me and my colleagues. Okay, so things were not going very well with the heavy metal style, so we start to switch over a little bit. So here you can see that we are more, more Hawaiian or well-behaved band. So you see that I have a ponytail now. You see? You have an overall and a ponytail, a more well-behaved look. And we start to change the style because we're not playing very much. So we're not getting a lot of shows, right? And then we decide to go in a different path that we make a lot of money, but I decided to stop playing because I couldn't stand it. And that was the end of it. See what happened to us? We became very popular. We had ballerines dancing in front of the stage and started playing Brazilian music, kind of axé, we call axé, right? The people from Brazil know. We started to get a lot of shows, but I couldn't stand that because I was a real rocker. I want to make my own CDs and everything, but went up on this. Although I was at the top of the ladders because I was the leader of the band. You can see that here, right? and you can see that the look was not very, I liked the long hairs and the bad guy style, much better. Okay, so that was to wake you guys up. So now I can get So I will talk about the heavy fermion superconductors. And I want to use, to describe these materials, I want to use the crystal field effect I described to you. Why is that? Because I want to talk about a family of heavy fermion superconductors that they show superconductivity in related structures. So, as the people have done with the pnictides, that they give the names using the stoichiometry, we do the same here. We have a 103, which is a cubic compound, And we have a 115 with serial transitional metal M that can be rhodium, iridium, cobalt, indium 5. And you have a 218 that is 2 serial transitional metal, 8 input. So it's 103, 115, 218. I want you guys to keep that in mind and to remember that the serial into 3 is cubic. Okay? And the 115 is a single layer of serial into 3 and transitional metal into 2. Single layer. 115, single layer. And 218 is a bilayer. 2 layers of serial into 3 by 1 layer of transition metal into 2. So why is that important? You know that we don't have many heavy Fermi superconductors, actually. So you nowadays at ambient pressure we probably have between 10 and 20 at most. So it's not much. And in this related structure we have 6, 7. Well, if you count the plutonium, most of them are in this related structure. Only in these 3 with cerium we have 6 if you count ambient pressure and under pressure. So, go ahead. Heavy Fermi superconductor at ambient pressure. I mean, if you compare to the metals or
Sure.
hydrogen.
So my question is
Why
it
is
because like people experimentally usually superconductivity arises when you suppress the magnetic order, right? So you don't see that because you're not able to tune these materials up to that point of of the critical point of the magnetic order, or because you do that but there's nothing there.
You do that in many cases, they're not in there.
Okay.
Right? How you have a lot of heavy Fermis that you tune there, you find Fermi liquid,
Okay.
and you don't see superconductivity for many other reasons. Right? Everybody wanted to see for a long time superconductivity in terbium rhodium 2silicon, right? Everybody say, well, that will be the first heavy Fermi superconductor, and they tuned everything they could and they didn't find it, right? They found another one that you know well, the terbium based heavy Fermi superconductor. But there are many, there are like 15 or something, and the large majority is in related structure. That's the point. Only in these 3 you have 6, right? Okay, so when you make a phase diagram from these compounds, you can, that's the 115, that's a single layer. The rhodium compound is magnetic. We dope it with iridium, we start to kill magnetism, and we find superconductivity. And the magnetism coexists with superconductivity, just like in the iron arsenide case. And when I mean coexistence, I mean by NMR, by μSR, by all the compounds you can imagine, like in the nuclides. When you dope it with the cobalt, we start to dope it with cobalt, you also found superconductivity in a higher temperature, right? So you have a very similar phase diagram, and if someone just looked to this, you can say, wow, that's amazing. That's kind of electron doping in one side and hole doping in the other one, right? It looks like that, right? Of course not, because it's isovalence distribution here. There's no doping at all. And even though you have exactly the same shape, right? So what's going on? Well, we don't know. What's driving the magnetic state to superconductivity? We can do the same with the 218, right? 218, here we're showing the 218 with rhodium, which has a little lower T nail, and then we dope it with iridium, and we suppress the magnetism, and at some point you start to see a dome that will kind of look like this. But then we have a spin glass phase that doesn't allow the superconductivity to go further. So it's a little bit different than the 115. So the DC is lower and the superconductivity is more restricted to the center of the diagram. Okay, the magnet states of these materials, they are different. They are local moment-like. Cerium window 5 has ultraferromagnetic order at 3.8 Kelvin, and it has the moment in the plane. I want to keep you that in mind, right? The moment for cerium window 5 is in the plane. For the 2 and 8, the moment is a little bit out of play. So based in what you have discussed, what do you be your guess? What make the direction of the moment change from the 2 compounds?
Just let you feel.
Couldn't hear you.
Let you feel.
Yes, right? It defines the direction of the moment. Okay, that's the direction of the field. Now I ask you, they have different nail. Could the crystal field change the nail too?
Sure.
Why?
Different symmetry.
Well, but it's not defined by J, the value of the nail,
Yeah.
by the interaction. So how could the crystal field change that? Remember that crystal fields not only change the energy, but change the wave function. And J involves both wave functions. The F wave function and the conduction electric wave function, right? So it can also change the wave. Okay, so when you look at the magnetizability of the 115s, comparing the 3 compounds, rhodium, iridium, and cobalt, then you have to remember that rhodium is a magnetic, and iridium is a superconducting, and cobalt is also superconducting, right? You can see that in AB plane, the magnetizability is basically the same. But if you look at the C-axis, we got an evolution going from the magnetic one to the superconducting. And as you go low here, larger is TC. Right? So when I saw that for the first time during my postdoc in Los Alamos, I came from a group where crystal fields were everything. So I look at that, and that's crystal field changing. But of course, I cannot say that here. Why? Because they are common. Right? Hybridization is important. And chain hybridization can do something similar here. Right? So I need to be careful.
So the level scheme in this structure, which one is it? Known?
Yeah, well, it's known now. Yeah, and I will show that. How the scheme changed and how the doublets changed. It is completely known now. Okay, so during that time we also tried to map TC as a function of something, right, in the material. And I found a relation between TC and T over A. The distance C, the parameter C, along the distance between the layers, and A. And we found that TC grows as more 2D become the material. It's hard to say that here, but more tetrahedron becomes larger as TC, right? But the question is, well, when you tune this, you are tuning everything. It's a very complex material. You're tuning the RTQI because you're changing distance. You're tuning the cone effect for the same reason. And you're tuning the crystal fields. So how can I separate these effects to try to learn something? How can I do that? Please.
You are choosing specific doping levels.
Yeah, using it.
You're using specific doping levels. Why you choose those to show up in your diagram?
Okay, I
Because
got the
there's a
superconducting.
goal.
No, I got the superconducting ones, right?
Yes, but for different dopants, you all have different superconducting temperature. But in your straight line, that diagram, you only choose.
No, it's the same. You see here? I got this point, and this point. No, I only these ones. I didn't use those. I'm just showing rhodium iridium here. Okay?
And cobalt.
Now I have cobalt iridium there. By cobalt iridium, I had a problem. See here? That I don't consider that because we had phase segregation at that time.
Okay.
But I got your point. Just to explain to you. All I need is, because I thought it was saying, how about rhodium? Why is not in the line? Right? That you mean, right? The magnetic ones. So was that your question? Why did I put the magnetic ones there?
Why you choose almost all 1.5 doping?
No, I have, you see this line here is the same one. So all of these points, they are in the line. All of these, I didn't use these ones. When TC started going down, so those are not in the line. So they are all, they are all here, right? the 25 and the 50 and the other 50. So they are all together here. So I didn't put all there because they will be all together here because silver change is very small.
Yeah.
So it's, I mean, I don't have much information there. I need to change a little bit the silver rate more than that. They will be all together here. Okay?
Thank you.
Please. But I didn't put the magnetic ones because they're not superconducting. And I think I know why.
The TMs stay also silver, right?
No. And I think it shouldn't. Because TN is strongly affected by the details of the crystal field. And I will try to convince you that TC is only affected by the doublet. I don't know if you agree at the end.
Yeah, so I was just wondering, so for example, the J value here, I would say if I don't change the A, I just change C. So should I expect to see a change in J also? Because in my understanding,
Well, we can change everything. That's my point. I cannot say anything. I just saw experimental fact that seems like TC follows silver rate.
okay.
Now I need to figure out why. I can say all of this. So as Raphael and Pierce and Musa, they can separate things very easily, right? Let's say, okay, let's just choose J equals 0. Come on. Oh, let's choose crystal field. Forget about it. They're up there. You don't need to worry about excited state. Sometimes you do records on planet. Okay, sometimes you have to consider the whole gold plate, right? But they can do that. So how? So how many of you can bore materials? No, the students. Yeah, or intermetallic ones or oxides. I mean, the experimentalists. How many of you can grow your own samples? Both of you. Okay, so if you have the same situation and you want to try to follow the evolution of J only, what would you do? No. Diluted will change J, but will change also lattice parameters. Will change silver A, will change everything. How? Yeah, well, okay, pressure, you change everything possibly. How can you get a reference? Think, I want to see, let me put the question this way. I want to see if rare earth rhodium 5 has a same J as rare earth iridium indium 5. Remember that rare earths are chemically alike, right? Very chemically alike. So I need to choose an ion that doesn't have condom. That's easy. Many of them, they don't have condom, right? It's only serum and deuterium. Which one doesn't have in crystal fields? Gadolinium, of course. So if I want, I can choose a reference compound and create, make these two compounds, all these compounds for gadolinium. When I do that, I have a tenale, of course, of gadolinium, it's ordered antiferromagnetically, but tenale doesn't change, right? We have a rhodium and iridium, and also we can go to our synchrotron and determine the magnetic structure of all of them, and we find some interesting results that I won't not discuss, but we do found that the tenale for cubic and tetragonal 218 and tetragonal 115 are the same. So we went from cubic to tetragonal rhodium, tetragonal iridium, 218 is our tetragonal rhodium iridium, and they have the same tenale. So if I have a very significant change of Fermi surface when you go from one to another, if I have a very complex evolution of the Fermi surface between the different compounds, that will change to TRKQI for any rare earths because the F electron are there localized. So for me, that tells that we don't have a change of first neighbor interaction when you change all these compounds. They're basically the same. Okay? So now I want to see if the crystal field is important, but not condom. What should I do? I go to the next one, right? On neodymium, it has crystal field, but it doesn't have a condom. So when you do that with neodymium, we find an evolution of the order temperature. That's TNAO for cerium 3, and that's TNAO for some of the 218s, rhodium and iridium and 115. So TNAO grows as a function of the same sequence that entropy recovered at TNAO decreases. So that means that the gamma 8, which is a quartet for neodymium, which is a ground state, and that's known, when you have the splitting of the gamma 8, TNAO increases. So the larger crystal field splitting, larger TNAO. So TNAO is being driven by the crystal fields. I have no condom here, right? So it's crystal field is driving TNAO, because I know J is not changing because I use the gadolinium, right? Okay, so I can do something like that. I can get, for some of the compounds here, I can get cerium, I can get gadolinium, neodymium. I also deal with terbium, I deal with many. I'm just simplifying things here for you. And you can look at the magnetic period, you can look at theta, right? Which is associated with J in a molecular field approximation, which is associated with the magnetic interaction, mean field, which is related to RKQI, in this case. But I can compare the evolution of theta with the evolution of TNAO. So what we can see here, and I want you to understand this very well. So for gadolinium, you have that both TNAO and theta are nearly the same among the different materials. But for terbium, you can see that the TNAO increases, and neodymium too, when you go from cubic to tetragonal, and for cerium it decreases. So when you go from cubic to tetragonal, TNAO decreases for cerium and increases for neodymium and for terbium. Some of you will say, what interaction we have in cerium that we don't have in the others? Condom, right? The condom effect is on for cerium. So you say, oh, of course, so it's a change in TK that is killing the magnetism for cerium. Why? Maybe not, because crystal field can have different effects in different J's. Right? So in order to try to understand that, we study all the magnetic structures and try to make a correlation between the magnetic structures and the behavior of the TNAO. And we find that compounds that shows the moment aligned along the C-axis, like neodymium and terbium, they show increase of TNAO. And the ones that shows the moment in the plane, they show decrease of TNAO. But again, who does determine the direction of the moment? Crystal field. So maybe only change crystal field for cerium, we can understand why TNAO decreases for cerium and not for the others. Okay, but in order to do that, we need to make some calculations to show that tetragonal crystal fields can act differently, because I showed it to you for a cubic, which is much more simpler, but tetragonal is a little bit more sophisticated. So I asked my colleagues in Campinas to do that, to make a very simple model that includes mean field RKQI and tetragonal crystal fields, to see if only this can account with the TNAO behavior that we found. And they found the following. Only with tetragonal crystal field, it is possible to go from a cubic compound. So we started a cubic compound. We chose the cubic crystal field parameters for